for the very interesting talk. And we can pass to the next speaker. So we have Mingyue, who received the BE in Communication Engineering from Beijing University of Post and Telecommunications in 2006, the Master of Science degrees in Electrical Engineering from Royal Institute of Technology in Sweden and from University of California, Santa Cruz in 2008 and 2010, and the PhD from the Mingyue Department of Electrical Engineering at University of Southern California in 2015. Subsequently was a staff to system design scientist with Broadcom in 2015-2016. He's now an assistant professor of electrical and computer engineering and an adjunct professor of School of Computing at the University of Utah. He received the IEEE Communications Society Leonard Abraham Prize for the best IEEE JSAC paper in 2019 and the best paper award in IEEE ICC 2015 and other awards. He's also served as an associate editor of IEEE Transactions on Communications, and is interested in the broad area of information theory, coding theory, concentration of measure and statistics with the application of caching networks, wireless communications, distributed storage and computing systems, distributed machine learning, and statistical signal processing. Mingyue, the floor is yours.
Okay, thank you, Filippo, for the very nice introduction. So can you hear me?
Yes, we can.
Yes. Okay, great. Let me share my screen. Okay, can you see my screen?
Yes.
Okay, great. Let's get started. Okay. Okay, thanks for inviting me for this very nice workshop. So I really enjoyed it. So today I'm going to talk a little bit on our recent work of the non-cooperative distributed bin scheduling framework for millimeter wave cellular networks. So this is a joint work with my collaborators, with my PhD student Xiang Zhang and my collaborators Shamik Shakar, Arup Buyen, and Professor Sneha Kasera. I would also like to thank my sponsors, NIL and NSF. Okay, so here is the outline of this talk. So first I will talk a little bit on the motivations, and then I'll go through the problem formulations and our main contributions. And then in order to solve this problem, I will introduce two approaches, right? They are pretty preliminary. So one approach is the game theory based approach. And the second approach is the distributed Q-learning based approach, right? And then I'll conclude this talk. So first, let's take a look at the motivations, right? So here, basically, what we're considering is a millimeter wave network, right? And the reason we consider this kind of network is because, obvious reason, right? They have much bigger bandwidth, and it can support much higher throughput. And the reason we would like to do some spectrum sharing is that here is an example. So for maybe we consider a warehouse, right? And then in the warehouse, we may have two networks. One network is for operations, and the other network is for the IoT devices, right? We consider both of them are like 5G private networks, right? Here, so both of them share the unlicensed millimeter wave spectrum, right? Okay, and in order to schedule the network, so we have two approaches. One is centralized, and the other is distributed or decentralized, right? And here we prefer the decentralized or distributed approach. The reason is obvious, right? Because we consider two different networks, maybe from two different operators, right? Therefore, the base station from them may not be able to talk with each other, right? So distributed approach is much preferred, right? From the technical point of view, so there is some disadvantage of the centralized approach. For example, it may not be very flexible, right? And from a security point of view, for the centralized approach, it may not be very secure, right? Because if we attack the central point, then the network might be gone, right? So it's not very secure. On the other hand, for the distributed network, right, it's very flexible, right? Every base station can do their own scheduling and do their own decisions. And there's no central point of attack, right? If one base station is gone, then the network can still operate, right? There's some advantage of this distributed spectrum sharing approach, right? So now let's take a look at our problem formulation. So basically, this is a problem that we're considering, right? So we consider a network that with multiple operators, right? They share the same radio access technology, but they cannot talk to each other, right? So no information can be shared among different operators, right? This is basically our assumption. We assume that the entire spectrum can be shared, right, by all the base stations. And in particular, consider the base station tower can be shared by different operators, right? For example, this is an example, right? So we have one base station, but these two transmitters are from different operators, right? This is also allowed, okay? And in this case, clearly we can see that although it's a millimeter wave scenario, but the interference can also be significant, right? For example, if you consider these two users, right? If both of them are trying to solve their corresponding users, right? In this case, we can see there can be a very big interference among them, right? Therefore, in order to do the bin scheduling and to do spectrum sharing can be very important for this kind of network, right? So our main contributions for this work are then as follows. So first, we propose a kind of new theoretical stochastic network optimization framework for this distributed network utility optimization, right? And one of the advantages of our problem formulation is that so it can cover a wide range of the basic scheme, right? For example, we can use this CSMA, CA scheme as a scheme in the action space, right? So this can be implemented, using the off-the-shelf device. Okay, and in order to solve this stochastic network optimization problem, so we propose two approaches to solve this approximately, right? Because we can see this optimization problem will not be simple convex or concave optimization problem. So there will be no optimal solution, or the optimal solution will be very hard. And we propose two approaches to approximately solve them. So one is based on game theory, and the other is based on distributed Q-learning. Okay, so let's take a look on how we can do this. So here is a basic network model that we consider. So we consider capital M base stations, and we consider KUEs, user equipment. And for the antenna model here, we just consider a simple sector antenna model, right? So in the main lobe, so this is our channel antenna gain, and in the side lobe, this is the antenna gain, okay? And so this is very important. We consider a frame structure here. So overall, we assume that the channel state information will not be changed within a frame, right? And we partition each frame into a few blocks, okay? And in each block, we have a number of slots, right? So scheduling can happen within the block, right? For example, if we consider a P-persistent protocol, right? In the first block, we can, each base station can access the channel with a certain probability, and then in the second block, they can access the channel again with a different probability and so on, right? And in this case, the probability can be a parameter to be optimized, right, in different blocks. Okay, so this is kind of very important. Without this block structure, so we cannot formulate our optimization problem. Okay, very important. And here is the problem formulation. So we don't need to understand the details of the meanings of the parameters here. Let's just understand the basic idea here. So for the objective function, it's just a network utility function. For example, U could be just fairness, and X here could be just the throughput within a frame or within a block. Okay, and here the first constraint is nothing but the average power constraint, which is natural. And then here this constraint is just a peak power constraint. So last one here is basically the action space, right? This is also very typical. So the action space, as we said before, it could be the basic CSMA, a multiple access protocol, or a slotted aloha, and so on. And here, in particular, we consider the game theoretic approach and also the Q-learning approach in this action space. Okay, so this is our basically the optimization problem that we want to solve. And from the formulation, you can see that we can use the seminal Lyapunov optimization framework to solve this problem. Right, there's nothing new there. Okay, and by using the Lyapunov framework, so naturally we have two virtual queues, right, to guarantee the constraint, right? One virtual queue is to guarantee the average power constraint is given by this formula, right? TD here is basically the data transmitted slot per block, okay? And another Q is to deal with the objective function. So we're having a function of average, right? Therefore, in order to solve this, we need to introduce a auxiliary variable gamma here, right? And this is to deal with this virtual Q is to deal with the auxiliary variable. Okay. So far, there's really nothing new here, right? The only thing new that is how we formulate this problem. Okay. And then after doing that, we can naturally decompose the optimization problem into two sub-optimization problems, right? And the first optimization problem is to deal with the auxiliary variable, okay? And it can be seen that this problem is convex problem, right? It's very nice. And in addition, so because of this summation here, so this problem can be implemented in a distributed way, which means that each base station can implement this problem, can solve this optimization problem on its own, and then we still have the optimal solution, right? So far, this is also kind of typical by using the Lyapunov optimization framework, right? Okay, so the hard part is actually the second sub-optimization problem, right? So this is our main challenge. We can see this problem looks like that, right? So here is some function of the power, right? It's a linear function of the power. And here is some function of the throughput of the network, right? X hat is the throughput. Okay, and we can see that, so this problem, because we have the throughput here, right, and also we're treating interference noise, therefore there will be a SINR term inside of this, therefore this problem cannot be solved, right? It's not convex, and it cannot be even solved in a centralized manner, right? But we consider a distributed way to solve this problem, right? How can we solve it? So this is the major challenge, right? So the two approaches we mentioned before, which are game theory approach or the Q-learning approach, is to basically solve this problem, right? And the Lyapunov framework can guarantee some performance gap there, right? So that's why we want to use the Lyapunov optimization framework for this kind of problem. All right, okay, so now let's take a look at how we can solve this problem. First, let's take a look at the game theory-based solution. So if we take a deeper look at the objective function for the second sub-optimization problem, we can see that, so it is in this form, right? It's a summation of a number of log 1 plus SNR and some power penalty here, right? This is kind of very typical, right? And so we can see, so this usually can be understood as a payoff function for a non-cooperative game, right? But there are many literature that is trying to solve this kind of problem using game theory, okay? But usually, so the key part here is the parameter alpha I and the gamma I here, right? So this kind of parameter is usually determined in a heuristic way, right? Or, people think, so one parameter may be increased over time, one parameter may be decreased over time, right? But they're all heuristic, okay? But here, the nice thing about the Lyapunov framework is that, so these two parameters, right? If you take a look at the framework before, so there are these Z and H, right? So they are basically the virtual queues, right? Okay, so basically by solving the first optimization problem for the auxiliary variable, so we can update our virtual queues. Therefore, we can determine this weight vector here, a weight parameter here, in an optimal manner. Therefore, we can guarantee some optimal performance of the proposed algorithm. Okay, so that's basically the non-trivial part of this. And by doing this, we can just use the Nash equilibrium approach to solve this game theory, to solve this game, and then obtain the algorithm, right? That will be our approach. And I will not go into detail of this. We can show the algorithm will converge under some condition, okay? And here are some simulation setup that we want to show here. So we consider 10 base station, 50 users, and they are distributed over 8 by 800 meters grid. And there's some other parameters here you can take a look. And for this fading, so we consider the Nakagami M fading for the millimeter wave channel. Okay, and then so for the baseline approach, right, as we said before, in the action space, we consider a non-game theory approach, right? We consider P persistent for where the probability can be a parameter to optimize, and also consider the CSMA approach in the action space, and also the parameters in the CSMA protocol can also be optimized between blocks. Okay. And in addition, we consider another genie-aided case. We call that the ideal case, right? This basically means that we ignore all the interference among the base stations. So this can be understood as upper bound of the performance of the utility function, right? Okay. And here are some example of the performance. We can see that the blue line is what we propose here, right? They're much better than the baseline schemes, and it's very close to the upper bound, which is the ideal case, right? Of course, this case consider the average case, right? And also the beam width is not very wide, okay? And performance can be, it's not very bad, okay? It's pretty good. However, if we take a detailed look at this, we can see that, because we consider average case, right? And it depends on the deployment of the network. Most of the user may not experience very heavy interference, right? But if that is the case, then the game theoretic approach may not be the best, right? So that's motivate us to consider another solution to solve the second optimization problem, right? So this is our proposed Q-learning approach. Again, so this is kind of the optimization problem we want to solve, right, in the Q-learning framework. So we consider that as a reward. Okay, so the key part for the Q-learning approach is how to formulate the Q-learning framework, right, the reinforcement learning framework. So here, the way we formulate the problem is that for the actions, obviously, that is just the power determined by each base station, right? And for the states, so this is the interesting part, right? So states, we formulate that as the interference, right? So here, we say for each user, so if we partition we quantize interference into intervals, right? If like this many intervals, if we say the interference falls into these intervals, and then we say the network is in the state of this interval called this J, okay? And that's basically the state, okay? And then for the reward, still something like that, right? Throughput, add some power penalty, okay? And then we consider this discounted reward function in the end, okay? And here we basically want to optimize this discounted reward, right? You can see that if gamma is very close to 1, then it's sort of like to optimize the average reward, okay? And for the updating policy here, we assume epsilon greedy updating policy, right? This is very typical. And for the updating of the Q table, so it's basically this formula here, right? The reason we think the Q-learning might be a better approach compared to the game theory is that if we consider the extreme case where beta is very small, then basically we're trying to optimize the throughput in a selfish way, right? So in this way, we can see that the best thing to do for the game theory is to pick the maximum power all the time, right? And this, we know that cannot be optimal when the interference is heavy, right? And here for the Q-learning approach, if we model this in the right way, so if every base station trying to transmit with the highest power, we can see in the next time slot, so this reward function will be very small, right? Then the value of the Q in this state will be reduced, right? So it's our intuition. And it turns out that, so if we operate this in a distributed way, right? So there's no anything shared, no reward shared, so it's not multi-agent reinforcement learning, right? And then we can see that, so the performance is kind of surprising, right? So here we can see that, so this is the quantization level of the interference. We can see even on the blue line, even we quantize interference into two states, then the performance is even better, it's still better than game theory in a heavy interference regime, right? And we can see that as the level of interference increases, the complexity will also increase, and performance can also increase, okay? Okay, so this is just for the reward function, right? Now let's put everything back into the Lyapunov framework. And here we plot some particular performance for some users who experience bad interference. And we can see that the Q-learning approach is outperforming with the game theory approach that we introduced before, right? In this simulation, it can outperform by 29%, okay, for some of the users, which seems pretty nice. Okay, and here it basically concludes my talk. Right. So here in this work, we propose a kind of nice stochastic optimization framework based on the Lyapunov theory. And so the nice thing of this framework is that it can cover a number of existing protocols as in this action space, right? And then we introduce two approaches to solve this problem in an approximate manner and with some performance guarantees. So we use the game theory approach and the Q-learning approach. Okay, and that'll be the end of my talk. Okay, thank you very much.
Thank you very much, Mingyue. And it was a very, very interesting talk. And now I can open the floor to any question from the audience. In the meantime, I have one. So can you elaborate a little bit more on the performance of your Q-learning based approach? The training, the time it took training, the solution, the time it took for the solution to converge, how well in your like even qualitative analysis or comments on the quality also of the solution, and if you have considered other types of reinforcement learning based, such as, I don't know, DDPG or other actor critic based.
Yeah, very good question. Thank you. Thank you. So here, basically, this figure shows the convergence time. So you see, this is the convergence time for the game theory, and this is the convergence time for the Q-learning. You can see sometimes it's even faster than the game theory. Okay, so it converts pretty fast for this simple Q-learning approach. Yeah, it's pretty interesting. And I think it's kind of practical. And for a second question, first of all, so we do not have convergence proof for this. So we don't know whether we can show that or not, because it's distributed. Usually the convergence proof is very hard. And we don't have the proof for the convergence of that. We just do the experiment and see it converges. So, and performance is pretty good and we're happy. But of course, we're going to try to show that can actually converge, but it's not an easy problem. Okay, and for a second question, so we did try some other approaches. So basically, because here what we consider is kind of a non-typical Q-learning approach, right? Because we restrict that each base station cannot talk to each other, right? We cannot share a word, we cannot share action, nothing can be shared, right? But now, because this basically consider all the base stations are from different operators, right? But we think if base station from the same operator, they may be able to share some information, right? So now this falls into this nice multi-agent reinforcement learning framework, right? So we're trying this approach as well, right? We didn't try anything about actor critic, so we have concerns on the complexity. But that is definitely a good future direction. And there's some other work that consider that solving very similar problems show promising performance for the actor critic approach, right? But we'll consider that in the future. That's a very nice question. Thank you.